Hello.
Hi, can you hear me? Hello, hello. Yeah, but I can't seem to hear anyone, I guess. So,
Hello.
hello. Yeah, I can hear you.
Hello. Yeah, can you hear me as well?
Yeah,
Hello.
yeah,
Fine.
yeah. Hi. Hello.
Hi.
Okay. Then I'll make you co-host and we can start. Of course, we have only 3 people today, but I've already started recording. So we can just start.
So, um,
Diganta,
yeah,
you hear me?
yeah, I can hear you, sir. Yeah. Right, I'll start screen sharing. So, there are only 3 people.
Oh, but he's sharing. Diganta, we can't hear you.
Hello, can you hear me now? Hello.
I can hear you, Diganta.
Okay. How about now?
I can hear.
Hello. Hello.
Yeah, I can still hear you.
Get that? Can you hear me?
Can yeah, I can hear you, sir. Can you hear me?
Okay.
Hello. Hello.
Can't hear you.
We can hear you.
Speak either Sudakshina or Dhruv Jyoti. Dhruv?
Hello. Can you hear me?
I think Dhrubajyoti is speaking right now.
One of the other people other than the speak so that we can test.
Hello. Hello.
No, I can't.
Diganta, can you hear me?
Yeah, I can hear.
Okay. Okay.
So I think yeah, I think it's probably on your end, sir. That maybe there's volume somewhere.
I'm going to give a piece of my mind. No, he should have set it up. Okay, properly. Yeah, now we are okay. Okay, I think the volume was turned too low. Okay.
Okay.
Okay. Okay.
I think there might have been a problem because the Zoom also got disconnected.
So I'll start.
Oh, you
Okay. So I want to do a few things today. One is I want to go into a little bit more details and
நாங்க தடுமாறணும்ல பார்க்கணும் வால்யூம் ஜீரோல இருந்து இப்ப நாங்க நாங்க இல்ல இப்போ சரியா பண்ணுங்க இங்க ஜீரோல வச்சு போயிட்டீங்க ஓகே இல்ல நீங்க இது ஜீரோல இருந்தது சரி
hello.
Yes, you can go ahead.
Yeah. So basically, I'll talk about a few things. One is some class of permutation invariance properties and what they are, and how they might apply to the ECAS-XZ system. The other is I want to. I think I've thought about a little bit more about how to decide which neurons to merge, and I want to go over some details of that. Okay. So maybe let me do that first. So how do we decide merge boundaries? Okay. So a few things. So suppose you have selected a particular output neuron. So you want a merge group, whose output neuron is going to be this particular neuron, right? And now you have several neurons in the previous layer. So you can have neurons like this, you can have neurons like this, and so forth, right? So remember the group that we're looking for, if say, for example, the group is something like this group is going to work really well only if the output of this neuron is a linear function of the inputs coming from the neurons we have left out in the group, right? So maybe I should also talk about the previous layer. Right? So for example, in this case, if this group works well, it means that the output of this neuron is almost linear in terms of the inputs coming in from here, in terms of the inputs coming in from here, the inputs from the outputs of these neurons, and in terms of the outputs of these neurons, right? So essentially, if this group works well, it is because there is a linear or this particular neuron is a linear function of these neurons outputs, these neurons outputs, and these neurons outputs, right? Okay.
No. Here, Diganta. So this is the eventual output, or I mean, the one that you circled here is the node that is part of this abstract group, correct?
Yeah, it is a part of the abstract group. So it
No, the
is
reason- Yeah, it's not the eventual output of your.
yeah, it may not be the eventual output of the network.
Yeah,
yes.
it's not. Okay. So what you're saying is to reemphasize to what I understand. So if it's a linear function of its inputs, then there is no loss of precision, and therefore the abstraction that is defined by this grouping is perfect.
Yeah, yeah.
Okay.
And so it's like flipping that on its head, the groups that we would want is where there is almost a linear relationship of the output of the neuron that we have selected with some neurons coming from the previous layers, right? So this is the basic intuition that we are trying to use, which is that a good merge will be one where are nearly linear relations between input and output, right? Right. So to choose a good
There's
merge group,
one question here.
Yeah.
From Rohan. Yeah.
so what's the question?
Yeah, no, I think he'll explain it. The question was to determine if a particular grouping will have a linear relationship. Okay, will be such that there will be a linear relationship between the output and the input. How do you do it? I mean, how do you figure out?
Right. So I'll come to that immediately.
That he will explain. But I think the point that he has just now made is that a grouping of nodes such that the output is a linear would be a good candidate for grouping.
Yeah. So conversely speaking, yeah. So basically, we are looking for so if we know that some neuron is a linear relation or a linear function of some input neurons, then we should form a group, right, around this neuron.
Yeah, the only caveat that I would put for this thing is I mean, of course you can use this as a criteria, but then you may then end up really merging only very few neurons. Okay, then your network size will be too big. So you'll have to balance your loss of precision with the size of the network that you want.
Yeah. So even here we will have control parameters which we can use to
yeah. Can you
control
yeah,
the size of
you
the
continue. I have to take a call. Yeah.
Okay, sure, sir. Yeah. Okay, so now let's come to the question which I think Rohan was asking, which is that how do we actually find so like if I give you the output neuron, so I've given you say this blue neuron, how do we find the input neurons which gives you a linear relation, right? And for this, what we will use is least squares. So let me just maybe copy this down here. So the question is, how do we find do we find inputs that are linear, and we'll use least squares for that. Okay, so
Diganta,
yeah,
can you just wait for a bit because the connection on sir's laptop has gone off? Actually, you can just continue here. Yeah.
Okay,
I have joined and we both can see from here. Yeah, but the thing is not being recorded because sir's connection has dropped.
yeah, but it is on YouTube, right?
No, it's not because sir's laptop has some issues with the Zoom. So Zoom is itself connecting. So he's not in the call anymore.
Just a sec then. Let me just.
No, Diganta, it's not an issue from your side. It's maybe the CMI Wi-Fi's issue or some.
So I'm just checking the YouTube live stream is still going, by the way. Okay, so even though,
EduRoam.
yeah,
No, I was talking with sir.
okay. No. So the YouTube live stream is still going. So
YouTube live stream might be going, but
right.
the Zoom call itself, sir, isn't in there, so he's not seeing your shared screen.
Okay. So right.
Yeah.
So let me know when I can
Maybe
continue.
issue with the CMI Wi-Fi with Zoom itself.
Let me know when you guys can see so that I can continue.
Yeah.
Can you guys see my screen now?
Yeah, you can go ahead now.
Okay,
I
sure.
think it'll be okay. So I gave up on CMI network. Okay, so I'm on my personal hotspot. So
Okay. Right. So now how do we find inputs that are linear? We'll use least squares method. So before anything else, I want to tell you mathematically what least square does. Least square is basically solve the following optimization problem. It will, so you're given a matrix M and a target vector Y. It will try to find X so that X M minus Y, right? The distance of like this is minimal, right? So in particular, if there is actually a solution to the equation xm equals y, then we know that the least square will give you that solution because it will find the fact that, okay, xm minus y is 0 and it will give you an x. So then least square will give you the. So if there exists x so that least square will give you the x. So how can we use this in our situation, right? So in our situation, we have this output neuron and we want to find inputs which give us so that like the output neuron's output values is a linear function of the inputs, right? And yeah.
What do you mean minimal with respect to what? Minimal over all the nodes? What do you?
So you're talking about this line?
Yeah, no. You minimize over all sets of nodes. So you just minimal with respect to what is what I'm asking.
No, so I'm not. So when I was talking in this section, I was saying what least square is as a mathematical thing. I was not talking about nodes at all. And I'm just saying that the least square problem is a particular kind of minimization problem, and there are solvers which can solve this. So this is giving some background on least squares.
Okay, so as an isolated problem, so you can find the minimal.
Yeah. So the idea is that it finds the closest solution to a linear equation. So it will find some x so that this equation where we're saying xm equal to y is closest to being satisfied. In other words, the distance between xm and y is minimal.
Okay. And
is this okay with everyone? Is what the least square problem is at least clear. So it is basically in least square problem, you're going to be given a matrix M and a vector Y, and basically you're being asked to find an X so that XM is equal to Y, or find an X which is closest, which gets XM closest to being Y, right? So it's kind of a generalization to solving a set of linear equations. If I ask you to solve a set of linear equations, I'm asking you to find an X so that this equation or this equality holds, right? But if there is no solution, then in least squares, I'm asking you to see, okay, find an X that is close enough, or that is closest of all possible values of X's. Is this okay with everyone?
yeah.
Okay. So now how do we actually use this? So remember that in our network, we actually, we had simulated the network on various different kinds of inputs. And we had got some, so let me just redraw some parts of this. And we have got some data from the simulation, right? So I had drawn 1, 2, 3 layers before, if I remember. Right, and we're looking at this output neuron, right? So we have now some data for the neurons involved over here, right? In particular, we have simulated this network on a bunch of inputs, and we have recorded a list of corresponding values which each neuron gets, right? So for example, for this output neuron, we have a vector. Let's call this vector, let's say Vy, which stores the list of values seen by the output neurons for the inputs and so on, right? So you can imagine you can have inputs X, X1, X2, and so on. And then the output of this neuron would be something for X1, something for X2, and so on. And this, if you pack all of these things into a vector, that is what Vy is, right? And similarly, you will have one such vector for all of the other neurons in the input side as well, right? So you will have a vector V X1 for this, Vx2 for this, Vx3 for this, Vx4 for this, and similarly 5, 6, 7, 8, 9, 10, 11, 12, right? So you have a vector containing the output values for each one of these neurons, right? So now let's say that Vy So let's say that the output of the blue neuron. So just to be sure, let me just number these neurons. Let's call this neuron the so we'll number these neurons 0 or 1, 2, 3, 4, and so on. And similarly, this will be 5, 6, 7, 8, 9, 10, 11, 12, right? And let's call this neuron the output neuron, right? Or you can just even call it Y for now. So if the output of Y is a linear relation of, let's say it's a linear relation of 5 and 6, just for example's sake. Okay. So let's say the output of Y is a linear relation of the outputs of the neurons 5 and 6. Then what do we have? We will have some coefficients so that Vy is going to be given by C5 x5 plus C6 x6, right? Is this okay with everyone? Yes, no?
Yeah, you're claiming that somehow you have found out, how you haven't explained, that you have found out that Vy is a linear relationship. See, but Vy, the reason it's a bit confusing is because Vy is not just a function of 5 and 6. It is in general a function of everything, the value of V5, V6, V7, V8.
Yeah, it is in general, but let's say that somehow.
What you mean by Vy being just a linear function of x5 and x6, which means that 7, 8, and are not contributing anything to Vy?
Yeah, so that is basically the example I'm taking in this scenario.
Okay.
Okay. So, I mean, whether or not that will happen is a separate question. For now, let's just keep it as a separate question. But let's say that somehow the output of Y is a linear combination of the outputs of 5 and 6. Then that will mean that Vy is going to be a linear combination of Vx5 and Vx6, right? This will be Vx5 and Vx6. Right?
What is the difference between x5, x6, and Vx5 and Vx6?
No, I was just trying to be consistent with the notation. I had written Vx1, Vx2 over here, so I just thought I'll make it consistent.
Yeah, so you mean x1, x5, and Vx5, they're the same. Okay.
Yeah. So it's just so.
Yeah.
Yeah.
There's a question, yeah. Yeah, but what he means is there is one more hidden layer, okay? What he means is, I think what he means, I mean, that's the clarification. So that's why I asked him. So there is, the question here is, well, there is a hidden layer 9 and 10, 11, 12. Okay?
Yes.
You are, throwing it away. So in the overall sense, Vy, the way Vi gets the value Vy gets determined is the values of all 5, 6 nodes of 5, 6, 7, 8, they get passed on. 9, 10 get something and that get passed on. But what he's saying is, I understand that somehow you determine eventually, okay, because you can express 9 in terms of this thing, etc., that Vy can then be expressed in terms of it, that you have come through analysis some way, that Vy is just simply whatever the value of Vy is, just some linear combination of V5 and V6. Okay, that he has somehow through this analysis he has come. to.
No, I mean, I'm not saying that I've come to the conclusion through some analysis. I'm saying that if that is the case with the network, then if it is somehow the case that the output of Y is a linear combination of 5 and 6, right? Then when we simulate it, the vectors we will see will also be linear combinations, right?
Of course, yes. But then
Yes.
how do you know? I mean, there is a question that is unaddressed. How do you know that Vy is indeed a linear combination?
Yes. So I'm coming to that. I mean, so basically from the vectors we're obtaining from the simulation, we will try to find these linear combinations. And then from there, we will basically see which neurons are linear combinations of what. But so far, if it is clear, then let me just rewrite this a little bit. We
But
can
what
read
if
it.
it is not? What if Vy is not a linear combination of Vx5 and Vx6?
So if it is not, then we can't really merge it and we can't really say this either. Right. I mean, or it won't be that good of a merge candidate.
If you merge only those that are whose output is related linearly as a linear combination of the input. Is that
Can you come again, sir? I think I couldn't hear what you were saying.
Yeah, you said that if it is not, we won't merge it. Okay?
No, I'm saying, okay, maybe won't merging it is a separate thing, but like I'm saying that it won't be as good of a merge candidate as something else which might have been linearly. So maybe can I just go ahead and explain this a little bit more and then
Please go ahead.
Yeah. So what I'm going to do is just I'm going to rewrite this. See, saying that this is a linear combination of x5 and x6, we can always just extend it and say that okay, it is actually a linear combination of all of these things where the other coefficients will be 0, right? So I can say something like sum over I, Ci, Vxi, right? And let's say that C5, C6 are only not the only non-zero coefficients, right? So this is another way in which we can rewrite it. And now when we are rewriting it as this, now we can actually pack these CIs into a vector, right? So we can say C1, C2, so on, up until how many do we have? C12. And similarly, we will have a matrix over here, right? The first row of this matrix will be Vx1, Vx2. And I'm just rewriting this equation. There is nothing going on over here up until Vx12, right? So what I'm trying to say is, look, if Vy is a linear combination of any of its inputs, any of the previous layer neurons, then this equation, let's call this equation 1. And let's call this C vector. Then there is a C vector so that 1 holds, right? Is this okay with everyone? So if it is at all a linear combination of any of its neurons, then there should be a C vector so that 1 holds, right? Or I should even say, if and only if there exists a C vector so that 1 holds, right? If it is a linear combination of any of its neurons, we can use the coefficients of the linear combination to construct C vector. Conversely, if we know that there is some C vector so that this equation holds, that means what? That it is probably a linear combination of each one of those neurons, right?
Yeah, that's kind of obvious.
Yeah. So now, what I propose, okay, so this is one point, and point number 2 is which neurons contribute to Vy correspond to the non-zero components of C vector. Right? So this is also clear, right? Because if any of these components is zero, then that means that in the linear combination, those components are not appearing. So now what I propose based on this is that
But the second bullet is also trivial. I mean, you just look at the C vector, and if there is any coefficient that is zero, that means that it doesn't contribute, isn't it?
Yeah.
More than that.
Right. So now what I propose to do is,
Okay.
so what we'll do is we will phrase the following least square query. Okay, where what we'll do is we'll collect this sort of a matrix of all of the previous layer vectors. We'll collect this Vy, and we'll send this query to the least square solver. We'll send M equal to this. Right? And we'll send Y equal to Vy, right? So when we send this to the least square solver, the least square solver is going to return it will return a C vector, right? So that this equation is closest to being satisfied. In other words, this is minimal, right? So now what we'll do is we will have a threshold value for this. So let's call this this value as the.
So is that clear? So I guess if I were to repeat just for my own understanding and perhaps the benefit. So what the least square solver will give is a set of coefficients for which the difference between the linear, between the actual value, okay, that Vy is in terms of those x1 through x12, such that, that thing is minimal. I mean, if it is exactly a linear relationship between Vy and these input vectors, those, the difference will be zero. Okay?
The difference will be zero, and then you have then you know that there is a linear relationship, and you know just by looking at the components which your input neurons should be, which neurons should be your input neurons.
Yeah, but if it is not, it will give you some coefficient vector.
Right.
But that's as good as you can do.
Right.
So this could use as a measure for determining which neurons you merge and not.
Right, exactly. And so we can look at this and decide the threshold values after, like, if it's less than the threshold value, we will do a merge.
Yeah. Okay.
And if it's greater than it.
Rohan, yeah. No. What do you mean the coefficients already in the network? I mean, the coefficients already in the net, these coefficients are different. Yeah, I mean, there's no coefficient in the network. I mean, you meant the weights. So this has nothing to do with the weights. I mean, they may have a relationship, but what he's saying is, given those weights, there is an actual relationship between the output, the Vy and the thing. But if that is not linear, then you already have it. Okay, that's a perfect situation. If not, it will give it'll tell how far these coefficients is some measure of how far, if it is not linear, that when you group them together, how far they are from the actual linear value. Yeah, okay. Linearly related value. Correct.
Yeah.
Is my formulation correct, Diganta?
Yeah. So it is basically saying how far is this particular neuron linearly related to all of like any combination of the neurons coming from the previous layer. And not only just that, if the linear relation is good enough.
No, but it's just not the previous layer, okay?
No, I mean previous layers. I mean,
it is not immediately previous layer. It
no.
can, as far back as you want.
Exactly. I mean all of the previous layers. So I mean this entire bunch of neurons, for example.
Correct. Yeah.
I mean to say this entire bunch of neurons.
Yes. So the input to this least square black box, minimization black box, it will be the entire network then.
No, it won't be the entire network. It will just be, okay, yeah, it will be the vectors coming from the entire network, yes. But at the end of the day, it's just going to be some matrix.
No, but that's where the confusion is, because you'll have to pass something to the least square minimal thing. What is it that you pass?
So we are passing these vectors, right? So from simulation, we're getting the output values of all of the neurons in all of the previous layers, right? So Vx1.
Wait a minute. Okay, so this is where maybe that point was missed. Okay, when you simulate it, you can simulate it only on a finite set of finite input set. So
Yes.
assumption here is that you're not computing it for all possible input values. So you're sampling the input for some particular set of inputs, and then that is what you're feeding in. Am I right?
Yes. So I do want to make this point clear that even if the least square solver gives you 0, it might be an artifact or some sort of lucky sampling that you have done. It might not imply that, like, the relation is actually purely linear, right?
That's right.
But,
no, that's right. No, because I mean, I want to remove the confusion of a solver. So far, our solvers like SMT solvers, LP
No.
solvers,
Yeah.
they're doing it for all input space, but that is not what is going on here. Okay.
No.
So that confusion I want to remove, because we called it as a solver, but it is something that is only working on a finite set of sampled inputs.
Right. So I mean, the least square problem, like a least square solver, is still a solver in the sense that there the problem space is itself finite. What we are not using it as a solve in a setting where we're using it for all possible input values, right? Like in some sense, the least square solver still looks at all possible combinations of coefficients, for example. But nonetheless, we are not giving it like some encoding of the network which looks at all possible values that can arise in the network. We are giving it some samples. So in that sense, yes, we're not using it like a complete solver.
Yeah, go ahead. Yeah. Is there any confusion here? Okay.
Yeah, so there is, so these are vectors coming from the samplings for each one of the neurons. Yeah. Okay, so now least square has returned these C's.
The reason this question comes up here, at least in my mind, is because in the last class, what you proposed of using Linsim for this thing was working on all possible inputs, okay?
No. We will use Linsim. This is just replacing the SVT part of it. So if you remember, we were talking about we're still talking only about step 2. Step 3 will involve Linsim
because
definitely.
that thing, okay. I think,
and that is where soundness will come in. Yes.
Yeah. Okay. Now the class. Yes. Okay. So you're proposing this only for replacing ACG because that you did not state in the beginning. Okay.
Yeah. So this is step 2. And don't worry, I'll prepare a document and send it to everyone so that you have all of these details. Of course, I'll upload this one to Moodle as well. Right? Yeah, so least square will return a C so that this one is minimal. So let's say the least square is returning some C, and let's call this value let's call it L for linearity, right? So the first thing we do is we will even do a merge. We will do a merge only if L is itself less than some epsilon that we'll fix, right? Some tolerance that we'll fix. Let's call this the tolerance on L, right? And secondly, if we see that, okay, L is small enough based on, whatever measure of smallness that we have decided, and this tolerance is something that we can tweak and try various values during verification and so on.
Here I have a question of what does merge here mean? Can you explain what you will do a merge means? What nodes will you merge here?
Yeah. So that is the second point I'm coming to. So first question is, do we even want to create a node like a merge group whose output neuron would be Y, right? So for example, if you look at a neuron, if you look at the network, we might want some merge group. We might want some merge group whose output neuron will be Y, right? Or maybe we don't want that. Maybe we want Y to be inside a merge group as an intermediate neuron and this one to be the output neuron, right? So given a network, there is a question of whether we even want to do a merge group whose output neuron will be Y, right? That merge group might look like this. That merge group might look like this. That merge group might look like this, right? But the point is that for all of these merge groups, the output neuron is Y. Do we even want a merge group with an output neuron to be Y, right? And that is what this L value is giving us, right? Because L is saying, look, no matter what combination of inputs you choose, no matter what you choose as your inputs for this particular merge group, if you choose your output neuron as Y, according to the simulation data that you have given me, the best you can do is this.
Yeah, but even now here there is so many different things that are left out, because even if you choose the node VY, the output node, how do you? You drew three different merge options, so you'll have to then ask for simulation for each of those.
No. Simulation is happening once in the beginning. We don't have to do a simulation for each one of these options.
No, I don't understand. Did you?
Okay. Maybe. Let me. Okay, I'm sorry, this is not clear, but I'll write some steps.
No, wait a minute. The input to the question here is, I don't think people at least the audience here understands. Okay.
Right.
Because in order to really do that least square minimization, okay, that you just now said, you'll have to fix the inputs.
Okay, yes. So
input neurons. And there are so many choices for input neurons, because why?
So when you say fix the input neurons, you mean the input neurons for our merge group. For example, if we don't need to fix the input neurons. Like I'm saying, for the least square minimization, I'm going to pass the simulated values for all of the neurons that could possibly be input neurons. I'm saying all of the neurons that are in the network and appear in layers before the output neuron. The only thing that we'll have to fix is the output neuron.
Yeah, but then what does the least square thing spit out? It spits out some boundary.
Yeah, it will spit out the coefficients, and by looking at the coefficients, we'll be able to get a boundary.
But that coefficient, it depends on the input layer. One layer. How do you know? Okay, there will be one set of coefficients if Vy is expressed in terms of 9 through 12, another set of coefficients if Vi is expressed in terms of 5, 6.
No, so what I'm doing is I'm actually giving the least square solver
Hmm.
all of the vectors for all
That
of
I
these,
understood.
right?
That is fine.
So now the least square solver can even give me something like this. It can give me non-zero coefficients for 5 and 6, and it can give me say non-zero coefficients for let's say this and this, right?
But
So-
no, still I don't understand. So
So there will be one coefficient corresponding to each neuron on each layer that could that has appeared in a layer before Vy.
yeah, so there'll be one set of coefficients for each hidden layer.
So there will be one set of coefficients for each hidden layer. Yes, exactly. And in particular, there will be one coefficient for each neuron coming in each hidden layer before appearing before the chosen output neuron, appearing before Y.
Yeah, but you gave the impression that, okay, that there'll be one set of coefficients, okay, one vector of coefficients. That's where the confusion was. Okay, so I'm.
No, so we're packing all of these coefficients into one vector so that we can like do this entire thing in one least square query. Right. We are packing all of these coefficients into one vector.
So that vector size will be as big as the number of nodes.
As big as the number of nodes you're seeing, there will be in all the layers coming before Vy. So in this
Okay.
case, it will be 12.
From that, how you determine what nodes you pack into a group is still unclear. Okay.
Right. So I'll come to that. Okay. So I think
So
it's a
go ahead
good
with the
idea.
question. Okay.
I think it's a good idea to maybe just let me give the steps and an example parallelly at this point.
But the real doubt for me, I mean, this got
Mhm.
clarified because I didn't know the number of coefficients. Okay, so here the number of your size, the vector of the coefficient C1 through C2. Okay, you have said C1 through C12. Okay, fine. That will include all. There will be one coefficient for every node
Right.
from input layer layer 0 all the way to whatever output that you select. Okay.
Yes.
Okay.
Yes.
Okay. Fine.
Yeah.
What was your question?
Diganta, I understand what you said that you'll get some kind of coefficient for every neuron. But if we reduce, say we reduce the size of the input nodes and give it to the least square solver, you'll get a different set of coefficients.
No, can you come again? I there was some echo.
Right. So if instead of giving all the neurons as the input to the least square problem, say we only gave say 9 to 12.
Right. Yeah.
So, since the least square solver is just doing a linear regression,
Yes.
it will spit out some other coefficients.
It will spit out some other coefficients. Exactly.
So if there is a case that one neuron is not contributing enough in the whole scheme of things, but if you reduce it to a smaller subset, it might happen that that neuron might input relate more with the output for a smaller subset.
Yes. But you'll also see another artifact in that case, which is that the distance that the least square solver will come up with will be very small, right?
Right.
So in some sense, suppose you only, so this is I think a good question. So say you only pass these many neurons to your least square solver, right? Sorry. So you only pass these many neurons to least square solver. Now two things can happen. The least square solver will return some coefficients. And let's say the least square solver gives you non-zero coefficients for this and 0 for the other two, right?
Okay.
Now, this can mean two things, right? It can mean that, okay, actually, Vy is just a linear combination of 9 and 10. In which case, the distance of like the minimal, the value of L that we have specified over here, the value of L will be 0, right? Or very close to 0. On the other hand, the least square solver can still give you coefficients where 9 and 10 have non-zero and everyone else is 0, but the value of L is large. See, in that case, the least square solver is telling you that, okay, look, this is not really linearly related to 9, 10, 11, 12, but if you still ask me to do a regression, the best possible regression is still one where 9 and 10 have the maximum contribution, right?
Yeah.
Yeah. So now in both of these scenarios, if you were to now go back and include the neurons from the previous layers, the coefficients can change. And those again represents two different possible, situations, right? One is C, that even though they're linearly related to this layer, it might still be the case that it's also linearly related to this, right? So in some sense, there might be two degenerate ways of expressing this output as a linear relation, right? So it might be that, just a linear combination of these two neurons works, and also a linear combination of these two neurons works, right? So in that situation, if you now were to pass all of these things to the to the least square solver, then the least square solver can give you these two. It can give you these two. It can basically give you either of these sets of coefficients, right? And for the both of them, the corresponding value of L will be small. And for both of them, you have a group of neurons which will give you something linear, right? Whereas again, if it is the case that L is large when you're only passing these, then what can happen is if you then pass these three things, it might be that, okay, this is actually a very good linear combination of these two neurons. In which case, when you pass all of the three layers, the least square solver will now give you coefficients where these is non-zero, everything else is zero, but L will now be small, right? So now in this case, you found a linear combination, right? So firstly, am I making sense? Does this sort of answer the question that you were asking?
Yeah, it sort of does. But my query was that if say 5 and 6 are very closely linearly related to VY, then we might miss out on neurons 9 and 10, which might be related, but not as good.
Yes. But that is I think a good point, which I think is like sort of like that is something that is not being addressed here, right? So maybe let me generalize the point you're saying. You're saying basically is what you're trying to say is that look, there might be various groups of neurons that are really related to Y, and we are not really doing anything to picking which group of neurons we want, right? Is that what you're saying?
Yeah.
Right. So for example, 5 and 6 might be related. Like in my example, 5 and 6, maybe 5 and 6 is a good linear relation. And 9 and 10 is also a good linear relation, right? So in this case, you would actually want to pick 5 and 6 as inputs, because then your merge group can be bigger, right? So your merge group can contain this layer and so forth, right? For example. So in that sort of a situation, you would want to pick 5 and 6, but here we are actually at the sort of mercy of the least square solver, because the least square solver will just give you any combination. You don't have any control over whether the least square solver will give you 5 and 6 or 9 and 10, right? And I don't know right now how we can force the least square solver to give us some set of inputs so that our merge groups are larger or smaller. I mean, I think you would want larger merge groups if you were looking for more aggressive abstraction. But we don't have any way of controlling, like in this situation where there can be multiple possible very good large groups, we don't have any way of controlling which one we want coming out from the least square solver. That is a good point, yes. I don't know how to do that right now. But do you have any ideas, Dhrubajyoti? Or who was asking this question?
Yeah, like I don't have any ideas right now. Like I'll think about it.
Yeah. I think it's a good point. Yeah, it's something that we're not doing, obviously.
I can't hear. I don't know if the rest of the folks on the thing can hear.
Sorry, so your voice is very low. Can you repeat what you're saying?
I didn't intend to speak to you. Okay, so yeah, maybe it's best that you. Okay.
Hello.
I don't know what the question you were asking for. Well, I mean, what you were.
Diganta?
Hello. Yeah.
Yeah, I'm just so sir did not understand my question correctly, so I'll just explain it to him once. And
Yeah, sure.
come back to you.
Make sure that everybody else who's on the thing also.
So just to explain my question was that if we consider all the neurons together, it might be that some neurons have a fairly significant linear relation with the output, and some not so much, but both fall under the tolerance limit. But because we use everything together, the two neurons which have the relation, the significant relation, dominate the others, and therefore we might miss out on the other. And Diganta just explained that, yeah, that is a problem which we'll have to figure out at some point.
Or I mean, that is something that we are not really controlling right now. So in some sense, sir, the idea is that, see, we can have a situation where the output of a neuron is given by two possible linear combinations. So maybe it is a linear combination of these two, or maybe it's also possible to give it as a linear combination of these two.
My question, maybe other people have this thing too. So I kind of don't understand how it is the least squares. So I mean, I do understand the situation that you brought out. Okay,
Mhm.
how do you even figure out if what the least square gives those two possible solutions? Okay, is a question that I don't even understand.
Yeah, we won't be able to, from the output of the least square
Because
solution,
it
we
is
won't be able
giving
to figure it out.
A single vector with
Yeah.
with everything. Okay. Oh, your scenario will come up only if the input is different. Huh? Yeah, if the input is different. Yeah, but I think Diganta is not proposing that solution. So he is saying, throw everything, all the nodes at it, and then it gives one single vector, okay, including all which has one coefficient corresponding to every node. And
Yes.
therefore, whatever is, yeah, I mean, you could pick, okay, what is not clear is,
That is what
okay,
I'm saying, yes.
yeah, so you will pick only those nodes which what it gives is, how should I interpret that? What it gives is some of them will be zero. So you can throw away some of those 0 ones. And if you keep all of them in, that will be the least away from the thing. But what is not clear to me is if this is the best thing, if this is the best grouping of nodes, okay, it's still not clear to me. Okay, why should this be the best grouping?
So best in terms of what is the question? So I think
optimal. There
I
could
think
be-
it will be the most optimal in terms of linearity, because least square guarantees like global minimality.
No, even there, I'm not so sure, because that is where Rohan's question comes into picture. Maybe I could partition it into, say, in these 12 nodes that you have, I'll be able to partition them into, say, 3 partitions with 4 nodes each. Maybe each of them could be good in its own right.
No. So I
them to be linear, as
Right,
opposed
right.
to if you throw everything in, it will give 8 in one and 4 in the other. Okay, where the distance is too large. How do I know?
No. So that is known in the sense that if there is, so this is strictly true that if you were to throw all 3 layers, the L that you will get will not be worse than if you were to throw any one particular layer or any subset of the layers, because any linear combination involving just this layer, for example, is also a valid linear combination when you throw in all of these 3 layers, right? So if you can already get a particular value of L with just this layer, if you throw in all 3 layers, you will still at least be able to get that L, but now you have a potential of doing better because you're now allowed to take linear combinations of these and so on. Right? So for example, if it is the case, that this is, suppose for if we throw just this layer, these 2 things are the linear combination that gives the best result. Now, if these 2 things were indeed globally the best result, when you throw in all 3 layers, you will still get these 2 things, because least square will give you the globally best result, right? You'll still get just these 2. Least square will automatically set the coefficients of all of these to be 0. Is that does that answer your question? And I think this was not the point which Rohan was raising, or no, the person was speaking previously was raising. I think he was saying that there is another measure of how good a merge group is, which is, or at least that's how I'm interpreting it, which is that the measure is in terms of size, right? So like if there are multiple combinations which do equally good in terms of linearity, but lead to merge groups of different sizes, then how do we choose between them? And and I'm saying that we can't, because least square solver itself is making that choice for us in some sense.
So, if say 9 and 10 are really that significantly related linearly to the output, is it
Yeah.
really the case that the least square will make all the others coefficient go to 0? Because then
Yes, if this is the globe, if it's the best possible relation you can do, then yes, that is what it guarantees. If there is an even better linear combination involving the others, then least square will give you that. If there isn't, then it will give you this itself.
But will the coefficients go to 0 or close to 0 or like somewhat smaller values than what 9 and 10 will get? And then will we have to apply some kind of threshold on what to consider in the merging sense and not?
Yes. So I'm saying, so let's say that if 9 and 10 being non-zero and the rest being perfectly equal to 0 is the best you can get, right?
Yeah, but I don't think that will happen for most of the cases.
That won't happen for most of the cases. That's correct. And yes, in general, we will have to apply some tolerance, right? So, but if it is better, like, see, okay. So if you have a case where, most of these neurons are being involved in some way, my guess is that in that case, the linear relation is not that great in the first place. Okay. Because, I mean, if you think about it, this layer is basically a linear relation. Like if you look at this neuron, it's computing a linear function of these four and then applying ReLU on it, right? So if it turns out that the best possible linear combination is some, like say 0.5, this 0.5, this 0.5, this 0.5, this, then that is basically being the least square solver is just saying that, okay, look, the best possible is not that great, and this is what the best possible is, right? So I think that in those cases, you'll see that the value of L will be large in itself. But if it is true that 9 and 10 are significantly related, and let's say that everything else, like let's say 11 and 12 are very close to 0, and that is giving you the close to the global minimum of L that you can see, if it is somehow true, maybe 9 and 10 is a bad example. Maybe let's say 5 and 6 are very significantly related, and 7 and 8 are giving you something very close to 0. And that is kind of close to the global minimum value of L. Then if you now introduce the previous layer, you'll also see that, okay, since that was the global minimum value of L, these will be close to 0 as well. That is the claim that I'm making. Does that sort of make sense to you? Or am I understanding your question correctly at least?
No, this is fine. So I have another more fundamental doubt about this.
Hmm.
So the least square query is
Mhm.
basically applying a linear regression, right?
Yes.
Okay. So in a linear regression, we always assume that the variables that you put in are
Right.
independent, even if they're sort of not in a real world scenario. But
Yes.
here, after the VX1 to VX4, we know for sure that from 5 to 8 and 9 to 12, the nodes are not at all independent of each other.
Yes.
That
Yes.
bigger issue because then the output of those 5 to 12 neurons can't actually be considered independently for the output of VY because it is 100% definitely dependent on the first 4 neurons.
Yes. So
So basically putting all 12 in and putting the first 4 input neurons in means the same thing because it will ultimately give you a linear regression between the actual input and the Y if they are linearly related, if the neural network has somehow produced a linear relation. But if not, then putting in all 12 when putting in the first four has like no different meaning for me.
Yes. So I see what your point is, but like none. So if there is the scenario where there are linear, if these variables are linearly related, you see they are related, right? But they're related through things like ReLU. So they're in general non-linearly related, right?
Sure, non-linear related, but related. So once I
But
choose
related,
for
yes.
the first input, it will affect how the 5, 6, 7, 8. Yeah, if they're not independent, even though it is a linear or non-linear relation, it doesn't matter because they're not independent at all.
Yeah, they're not independent at all. Yes, but what I'm trying to say is that look, huh?
Your basic assumption for a linear regression, which is being used by the least square method, fails that point that they're not independent at all.
Yes. And I mean, at the end of the day, this is in some sense a heuristic, right? But what I'm saying is that, like, if you were to just so okay, fine. So if we work under the assumption that they are in some sense independent and see what we get and then merge based on that, right? Because if it does turn out that somehow there are some linear relations between them, then nonetheless the regression result should go to 0 even if they're dependent. So let's say, for example, this 12 is a linear relation of 5 and 6, and this one is also a linear relation of 5 and 6, right?
Yeah. So let me give you a scenario of just one sec.
Yes.
So if you think that, so say 5 is related to the 4 inputs in a non-linear fashion, but the thing is, are all the neural networks that we are working with all have ReLU constraints? Okay?
Yes.
So the negative values will go to 0 and the positive ones will go to X. Right. So
Yes.
if like whatever relation that 5 will have with the first 4 can never be considered 0 at all. So like in any scenario, we can't consider the neurons in the hidden layer to be independent of each other at any point. Because say if the least square query gives out that the Vx1 and Vx2 are linearly related with the output, say, and X4 and X5 are not, sorry, X3 and X4 are not, then there will 100% be a scenario where some of the neurons from the next hidden layers will turn out to be linearly related. Because
Yes.
obviously there will be some input values where the additions don't go to negative and remain X, and therefore it is supposed to be linearly related as well. But once we know that the input variable itself is linearly related, do we really need to look at the next neurons in the hidden layer? Because that's just a combination of the first neurons anyway.
Okay, sure. So that actually makes sense. That actually makes a lot of sense, in the sense that if we were to say, say we just throw this layer at the least square solver, right? And we get like a good linear relation.
Yeah.
So you're saying that we can stop there, right?
You can stop there, but like putting in all just doesn't make any sense, because if this was the case where all the 4 or even a subset of the 4 are linearly related, then 100% there will be a case that some of the hidden layer neurons are linearly related. So we don't even have to look at that. But if we do by this thing, that the first,
so my question is this: can you so like, is it possible that, for example, there is a linear relation of the output between these 4 neurons across multiple layers? Can that happen?
Yeah. So we are running into we've gone 1 hour 15 minutes. Okay. So we'll have to pretty soon put end the session. So we'll have to continue this discussion. So what I'm proposing is you make a document, Diganta, Okay, so there was all this is addressing task 2. Okay, the step 2 of determining the boundary. Okay, we proposed a rough solution last time. Okay, and this is yeah, well, you can say an extension. No, because there it was somewhat clear. Okay, we were iterating through some subsets of nodes and so on. So it was clear there. Okay, whereas here, at least to me, it is not clear. Okay, the criteria is not clear yet. Therefore, what I propose is we should document. That is, we will document the two solutions, okay, to the extent that with some gaps, okay, so that we can have that as the working document. Everybody contributing to yeah, go ahead. Yeah. So that is from a logistics. So the question is, one's question is, why can't we use the traditional? Was he Diganta? Not that I'm not trying to say that you didn't pay attention. See, the thing is, of course you could use that, okay, but that is limited, among other things, to merging only yeah, the same layer thing and so on. So whereas here we could decompose, or we could compose it across network, I mean across layers, and theoretically speaking, you could draw that boundary every which way you want, okay? And you could use Linser, for example. I could, I mean, then it will produce some approximation, linear approximation of that. Now, this is a refinement. What Diganta is doing is a refinement. That was the reason why we went beyond that, okay, is of course, in our proposal, you could have that one also, okay? And I try that, and this was a slide. This was a different thing that we could explore and to see. And since this fits in well with Linsim and De Pauli kind of a thing, because it is able to do this kind of linear optimization, okay, approximation thing. And therefore, that was the reason that we were considering that. Okay, so I think we are coming to the definitely 5 o'clock, limit. Beyond that, and is my proposal agreeable? Okay, Diganta.
Yeah, I'll definitely prepare a document.
Yeah.
It's also, who was the one who was asking this question? Because I think if you have some time, then I can call you, Rohan, right? Can we chat briefly, because I want to understand the point that you're trying to make. I don't think I understand it fully.
The last question that he asked, or the question that he was discussing earlier?
No, the last question regarding the neurons, the inputs themselves being not, they'll be dependent on each other, and how that leads to some issues.
Yeah, we can discuss that. I mean, I think his question was simple. Why do all this thing, and just why not use node merge abstraction? The previous one. Okay, that you can actually, do you guys can do one with him too, yeah. And then figure out what the thing is. Yeah, so that that will give your feedback into it, and that we can figure that thing into the thing. So before next class, we will definitely have some working documentation of the proposals that we have for node merge, and then we will take that forward. Okay, Diganta?
Yeah.
Okay, thank you. Diganta, we are meeting at 5, huh?
Yeah. So same link or?
Yeah, I think we can use the same link. you know,
Sure.
but I'll have to go to my.
Yeah, I'll leave this meeting and rejoin at 5.
Yes, yeah.
Also, Rohan, what time in the evening works for you today? Is any time in the evening good for you today? Sure. Okay. So
Anytime,
Yeah,
I'll
you
call
can,
you.
any mutually convenient time that you two will coordinate. Is that okay?
Yeah. So you're asking me to record the meeting.
no.
didn't
He
understand
just
the
said that
question.
any mutually convenient time is fine. So I'll just message you on WhatsApp. And then once your meeting is done with sir, then you can